Hello everybody. Today we'll be covering rectilinear motion under motions of particle. Rectilinear motion is a motion along a straight line or a path. For example, we have this water rushing out of a tap. The water is moving straight down, following a straight line like this, hence it's undergoing rectilinear motion. Next, we have this car moving along a straight road. There is no bend or curve on this road, just a straight line, hence the car is undergoing rectilinear motion. The same thing goes for this plane as well. From the beginning to its destination is just a straight line, hence it's also undergoing rectilinear motion. And lastly, we have this ball. Let's imagine the ball is falling from the top of a building or something, and it's going straight down like this. We'll say that the ball is undergoing rectilinear motion because it's just going up and down and following a straight line. Now we have another type of motion that we're going to cover, and it's curvilinear motion. This is just like rectilinear motion, but now instead of a straight line, it's moving along a curve. We have this car, for example, moving along a bent road like this. In this case, because the path is bent, we'll say that the car is undergoing curvilinear motion. We will go in depth in curvilinear motion in our next video, but right now we'll be focusing on just rectilinear motion. There are two instances that can occur when dealing with rectilinear motion. We have constant acceleration and non-constant acceleration. When the acceleration is constant, we have to use the equations of motion. Most of you guys are probably familiar with these formulas and how to use them. But if you aren't, that's okay because we'll be going through some practice problems later. Now you're going to cover for when the acceleration isn't constant. That is non-constant acceleration. You may be wondering what non-constant acceleration is, and it's just acceleration written in terms of another variable. This variable can be t, time, x, distance, and v, velocity. For example, we have this. This acceleration is dependent on t, time. We also have this. This can be another example of non-constant acceleration. This one is dependent on distance, x, as you can see here. And this one is dependent on v, velocity. When we are given this non-constant acceleration, there are two steps needed to solve them. Firstly, we have to identify which formula to use, and secondly, we then have to integrate the formulas from its initial points. For the first step, we have to identify which formula to use, and we have two formulas that we can choose from. The first formula being acceleration equals to change in velocity over change in time, and the second one being velocity times change in velocity over change in distance. You are all probably familiar with the first one. It is written in respect to t, while the second one is gotten from combining the first acceleration formula, this one, with the formula for velocity, which is v equals to change in distance over change in time. Let me quickly show you how we can get this one. Okay, so first of all, we have our velocity formula, which is equals to this, and we have our acceleration formula, which is equals to this. Then we're going to cross multiply our velocity formula and have v dt equals to dx. Then we're going to single out the dt and have dt equals to dx over v. Now from this one, we're just going to have a equal to dv over dt. Therefore, a equals to dv times 1 over dt. And from here, we have that our dt equals to dx over v. So I'm just going to quickly write that as a equals to dv times 1 over dx over v. Therefore, a equals to dv times v over dx, which is v dv over dx. So this is how we get our second formula for acceleration. And it is written in respect to x, distance. Now, depending on what the question asks for and which variable we have, we'll choose between the first formula for acceleration, this one, or the second one, this one. And then we'll integrate our chosen formula from its initial point. Now we have our formulas pinned down. We are going to have to integrate the formulas from their initial points. And I'm going to show you how to do that for the two formulas. Okay, so for the first formula, we have this. So we're going to just write it down again. And we're going to cross multiply. So we have a dt equals to the v. And because the a isn't constant, it's going to be treated as a function. And we're going to treat it as a function of time because of this t here. So we're going to treat it as a function of time. So we have functions of time on one side and functions of velocity on one side. Now we have that. We're now going to bring our integral sign. And remember, we have to integrate from its initial points. So we're going to put t0, t, v0, and v. Now that is going to give us, and because the initial time most times is going to be 0, like before you start anything. So we're just going to write it as 0t f bracket t dt equals to v 0. This is going to be written as this. Now, we have integrated our first formula from its initial point, and we got this. Okay, now we're going to do this for the second formula. For our second formula, we're going to do the same thing and write it down again, this formula, and cross multiply. So we have, and then cross multiply a dx equals to v dv. Now we're going to write our a as f of x because we want all the x's on this side and all the v's on this side. Now we're going to integrate. And remember, we're integrating from the initial point. So we have this. We now have integrating this give us, we're going to write this side again, just like we did for the first one. And this is going to give us v squared over 2 v and v0. That means for our final answer, we have something like this. Okay, now I'm going to write that down neatly. Now, for our two formulas, for this one, we have this, and for our second one, we have this. Some people will advise you to memorize this, but I don't think it's necessary to memorize it if you can just easily integrate it each time. And we'll be heading straight into examples to show you how to apply these two steps. Remember, our first step was to identify the formula to use and then integrate it. So we'll be heading on to examples to use the steps. For our first example, we're going to be doing this question. So the velocity of a small sphere when entering a big oil tank is 60 meters per second. And the resistance to motion in the liquid causes the acceleration to change as a equals to negative 0.4 velocity cube. Determine the velocity and position of the sphere after 4 seconds. Okay, so we have to remember our two steps. The first step is to identify which formula to use, and the second one is to integrate the formula from a starting point. So we have two formulas for acceleration. We have a equals to change in v over change in t, and we have a equals to v change in v over change in x. This one is written in respect to t, and this one in respect to x. Now, from the question, we have our initial velocity at 60 meters per second, our acceleration as negative 0.4 velocity cubed, our time as 4 seconds, and we're looking for our final velocity at 4 seconds. The first thing we're going to do is to break down our acceleration because it is a non-constant acceleration. And now we're going to think, which formula are we using, the first one or the second one? Now, we're going to use the first one because they gave us our values of t, and we also know that t0 equals to 0. So we have everything for the integral part. Whereas if we use this one, we don't have x and we don't have x0. So we'll be going with the first one because we have everything. We have both t equals to 4 seconds and our initial time as 0. Now I've identified the one we're going to use. We'll go ahead with our integration. We'll do minus 0.4 v cubed, which is our a, equals to the v over dt. Now remember that we're meant to try and put like terms together. And right now, like terms aren't together because we have dt and v here. That means we're meant to get this v over to this side. That's what we're going to do. So it will be dt equals to minus 1 over 0.4 v3 dv, which equals to, we're going to do minus 1 divided by 0.4, which is going to be minus 2.5 v, because we're bringing this 3 on top, it's going to become negative 3 dv. From here, we're going to pull out our integral signs. Bring out the constant first. And remember, because we're integrating from the initial point, so this is going to be 0, our t0, but this is going to be 4. And then this is going to be v0 and v. Okay, now integrating this is going to be minus 2.5 v minus 3 plus 1 over minus 3 plus 1. We're going to bring our v and v0 all equals to, integrating here is just going to give us t. And if we plug in our t as 4 minus 0, we're just going to get 4. So I'm going to write this as 4. So this is going to be minus 2.5 v minus 2 all over minus 2 v0. Now we can cancel these 2 out, and that's going to give us 1.25 v minus 2 v0 all equals to 4, and that's going to be 1.25 v minus 2 minus 1.25 v0 minus 2 all equals to 4. Now from here, we have that our v0 equals to 60 meters per second. So that's just going to be 1.25 v minus 2 minus 1.25, 60 minus 2 equals to 4. Bringing that all up here to create more space. We have 1.25 v minus 2 equals to 4 plus 3.47 times 10 raised to power minus 4. V minus 2 equals to, we have to add all this up together. Basically 4, it's like 4.000347. So we have v minus 2 times minus 1 over 2 equals to this. Raised to power minus 1 over 2. And that gave us v equals to 0.559 meters per second. Easy. So from here, we're able to get our final velocity from this question. Okay, so now that we're done with non-constant acceleration examples, we'll be going into constant acceleration examples. And like I said earlier, we just have to use the formulas, the equations of motion to be able to solve it. And yeah, that's actually all we have to do. Now we're going to solve this example together. A car is traveling at 48 kilometers per hour when the traffic light 90 meters ahead turns yellow. The driver takes 1 second to react before he applies the brakes. What constant rate of deceleration will cause the car to stop just as it reaches the light? So firstly, I'm going to show you a visual representation of what this question means. So firstly, we're going to write down the values that they gave us. So they gave us initial velocity. They also gave us final velocity because they said come to a stop, right? So that means it's coming to rest. And that means the final velocity will be 0. And we also have the distance. And we're looking for A, acceleration. Now, just from the variables we have here, what formula do you think we're going to use? What equation of motion do you think we're going to use? From everything we have here, because we have initial velocity, final velocity, distance, and acceleration, I think we're going to use this one. But if we're using this one, then we have one variable that is missing, which is our initial distance. And how do we get our initial distance when we are also looking for acceleration? Well, it's very simple with this question because they said that he takes 1 second to react. That means his initial distance starts at 1 second. If here is 0, here, where the initial distance starts, is what? Well, we also know that his initial velocity is 48 kilometers per hour. That means that's the speed he started moving at this point, right? So we need to know how many meters he moves per second. Like how many meters does he move after 1 second? So we have to change our initial velocity to meters per second, and that's very easy. So do 48 times 1,000 all over 3,600, which will give us 13.33 meters per second. Now we know that his initial distance is 13.33 meters because he moves 13.33 meters per second and is starting just after 1 second. So now we have everything. Let's write down now. And we can simply plug in everything into our second equation. Therefore, A is going to be minus 1.16 meter per second squared. And as you can see, this negative sign goes in line with what the question asks for because it asks for a constant rate of deceleration, not acceleration. And we all know that deceleration is negative acceleration. So yes, we are done with this question and we are done with rectilinear motion. Our next video will be covering curvilinear motion, still under motions of particles.